to just consolidate what I've seen so far by applying these concepts to some specific models, and by resorting to your engineering skills through what is called the rheological models. What are rheological models? Rheological models are mechanical models which are very understandable by engineers, because engineers are used to mechanics, and that just by some translation of words can be then related to constitutive equations. Okay, so in terms of that, we are going to play around all the concepts that we are seeing about this thermodynamical framework for constitutive equations. So let's start talking about what is termed elastic element. What is an elastic element? Well, typically it's in a spring, a spring that you are very familiar with. And a spring is something that demands a force, and under this force you have a displacement of the end of the spring, delta. And this force is proportional to the displacement through a constant which is called the constant of the spring. Okay, that's something that you will understand. Okay, what is the translation of this mechanical model into a rheological model that we are going to term elastic model? Well, instead of force, we talk about force per unit of surface, the stress. Instead of displacement, we talk about elongations per unit of length, so that's a strain. But the concept is the same. So we apply in a stress and we get a strain, thinking in the mechanical model, and this stress and that strain are proportional to a constant. To a constant which is the Young modulus in 1D, or in the more general case, the tensor, that fourth order tensor that then can be reduced to two variables, that is the elastic constitutive tensor. And again, the stresses versus the strains are proportional. The slope of the relationship is this E or this C. Double strain, double stress, triple strain, triple stress, both in positive or negative sense. So far, very easy. So let's try to formulate this elastic model, we have done already a certain number of times, in terms of what we have seen before. For instance, what about the stress-driven model? We know. We define the free variables as the stresses. The internal variables, it's an elastic one, empty set. Okay? And the remaining variables, the strain and the Gibbs potential, which are a functional of some internal variable, whatever, there is nothing here. Okay. The Gibbs energy is 1/2 a quadratic form of the stresses in terms of the inverse of the elastic modulus. That's it. And the dissipation is 0. We know that. Okay? If we prefer going to a strain-driven model, then just we take the free variable, the strain. Again, the internal variable set is empty. Dissipation, or the dependent variables are the stresses and the free energy. And the free energy itself, for an elastic model, a linear elastic model, we define this function as a quadratic function of the strains in terms of the elastic tangent constitutive operator. Again, by manipulating all that and using the methods we have seen before, the dissipation in most cases is 0. Okay? So somehow this is the summary that we take of the main ingredients for an elastic model. Okay? So far, so good. Let's go to next step. Imagine a dashpot. You know what a dashpot is, right? It's something that when you try to apply a force, the force that you apply depends only not on the displacement of the end, but on the velocity of the displacement. So for a dashpot, just moving the end of the dashpot very slowly at slow rates demands a very little force, theoretically no force. If you try to put just a sudden velocity, so a high velocity, high rate of the displacement at the end, then you would notice a important resistance to that. So you have to apply high forces. What does it mean? That the mechanical law of a dashpot is that the force is proportional not to the displacement, but to the rate of the displacement, to the velocity of the end. And the constant of this proportionality is something that is called a viscosity. Okay, that depends on the geometry and so on, but there is a constant, a viscosity-like property that depends on that. And then, of course, we can say that the velocity, that's something that we are going to keep in mind, the velocity at the end of the dashpot is the inverse of the velocity of inverse of the viscosity times the force. Okay, so that's the mechanical equation of the dashpot. Why not to just think of a model which is a rheological model based in this mechanical dashpot? This is a viscous model in which we have something that instead of displacements we'll talk again in terms of strains, and instead of forces we'll talk of stresses. Okay, and then similar to that, then we would like maybe to recover a thing like that, so that the displacement, the rate of the displacement, well, the rate of the strains is 1 over the viscosity, which is a property, material property, times the stress. Okay? But let's formulate this model in terms of what we have seen. Okay, let's define an internal variable now that we will term beta, which is precisely the full strain. So the strain of the dashpot is now considered an internal variable. Okay? So beta dot equal 1 over eta times sigma can be considered what? An evolution equation that gives the evolution of the internal variable in terms of sigma, sigma being the free variable. So, in principle, the model in a stress-driven environment could be considered like that. Let's consider the stresses as the free variable. Let's consider an internal variable set, which is precisely the strains. In 1D, it would be the strain, but in many dimensions, it will be the vector or the tensor of strains. Okay? And then the remaining variables are dependent. So the strain itself and the Gibbs potential are depending variables. Okay? Well, what about the Gibbs potential? Can we guess the Gibbs potential for that? Well, we know that since this is a stress-driven model, the derivative of the Gibbs potential, which will depend on sigma and beta with respect to sigma, has to return the strains. Remember, in a stress-based model, so, well, if that is so, why not to consider the free energy as definition of free energy to return that as sigma times beta? In fact, we check that by differentiation of sigma, this function with respect to beta, with respect to sigma, we return beta. So this is a good candidate to represent the Gibbs potential. Okay.
I don't understand why the strain is an internal variable and also
No. In fact, I consider. We'll see that at the end we consider both are the same. So just consider one. In other words, let's consider one internal variable whose evolution equation is like that. By comparison with that, we are guessing that at the end of the day, we have to obtain that this beta is precisely the strain. Okay? In principle, we're done. Okay? So this is a quite aseptic variable environment in which I've chosen, that's a case in which we just guess what is the Gibbs potential in virtue of what we want to obtain from the constitutive equation. This, in fact, is the constitutive equation. Okay? So what does this constitutive equation says? And I'm now talking for you. The constitutive equation says what? If I take this constitutive equation, what is the constitutive equation? Epsilon is derivative of this with respect to sigma, which is beta. So if I start from that, and this, I obtain this as a result. But it's consistent with the model I want to do. So probably, after some little iteration, one should be able to say, well, if I want at the end of the day that epsilon is equal to beta, because physically it's the same, or mechanically it's the same, then I have to take that as the Gibbs energy, and then, as a consequence, the constitutive equation says that the strain is the derivative of the free energy, the Gibbs energy, this potential with respect to stresses, and this is the constitutive equation. Okay? It's a little special constitutive equation, but anyway, it's something that returns the strains, which are a dependent variable, in terms of the other variables. In that case, sigma doesn't appear here. Okay? By the way, what about dissipation? That's important, interesting to see. What about dissipation? Well, we know that dissipation is the derivative of the Gibbs energy with respect to beta times beta dot. Okay, you know the dissipation, we had it here, the dissipation in these general based inelastic models, the dissipation is the derivative of the free energy with respect to internal variable times the rate of the internal variable. Okay, so let's go back here and see that as a consequence, in the context of the thermodynamic framework we have visited, then the dissipation should look like that. Okay, but look, sigma times beta dot, we can rewrite that considering that beta dot, in terms of the evolution equation, is 1 over eta times sigma. So let's replace it. And see the dissipation is 1 over eta, the viscosity, times sigma, you see? And this has to be greater than 0. Well, what is the consequence of that? Well, one tensor, double dot product times itself, it's always positive. Okay? Just to a little proof of that is that if I have one tensor, okay, A11, A12, A13, A21, A22, A23, A31, A32, A33, times itself double dot is the sum of IAJ times, or IMJ times AJ. IAJ, that this is the repeated indices, so we have to take this one and multiply times itself, plus this one times itself, plus, so this is A11 squared, plus A12 squared, I13 squared, plus I31 squared, etc. All these terms are positives or not negative, so the sum has to be non-negative. So this is greater or equal than 0. And the product of this times this has to be greater than 0. What does that mean? That the viscosity has to be greater than 0. So you see, we didn't know that at the beginning. I recall that the dissipation, that equation, is always the expression of the second principle of thermodynamics, which somehow is an inequality that discriminates processes that could be feasible, physically possible, or non-physically possible, unfeasible. Okay? So this says that for a dashpot be physically possible, that the formation of a dashpot take place in physically sounding grounds, the viscosity has to be greater than 0. And how does it matches our perception? Imagine, no? Imagine you have a dashpot. So a dashpot with negative viscosity means that when you push it, the dashpot moves upwards. And when you pull it, the dashpot moves downwards. So that's something that could happen. It could happen maybe in another universe. But in our universe, we know that this experiment cannot be done. You see here a clear example of what the dissipation equation, what is the role of dissipation equations, dissipation in expression in derivation of constitutive models. It places limitations on the material parameters. So it says that, okay, you can derive a viscous model like that, but it's not feasible physically meaningful, that the viscosity that you take by this viscous model is negative. Viscosity is only physically, has only physical sense if it's always positive. Okay? Okay, so let's go a step further. And now try to do the same model, but trying to represent that in a strain-based framework. That one was in stress-based, right? The stresses were the internal variables. Let's do that in strain-based, strain-driven, okay? So the strain-driven model said, okay, the free variables are the strains, and the internal variables are beta, okay, which is the strain too. So the same variable cannot be at the same time free and internal. That's a contradiction, okay? And that's why this model cannot be formulated in a strain context, in a strain-driven context, okay? That's why we have both, because we are able to formulate a rheological model of a dashpot or dashpot-like model in a stress-driven context, but it's not possible to formulate that in a strain-driven context. What is the consequence of that? Let's imagine that we consider that beta and epsilon is the internal variable, the free variable, and beta is the internal variable, and then in that context the stress and the free energy are dependent variables. Then how would be the free energy? The free energy, which would be rho 0 g plus sigma epsilon minus sigma epsilon, which is sigma times beta, rho 0 g, I recall that rho 0 g is sigma times beta, right? So now taking g as sigma times beta minus sigma times epsilon, which is beta too, those is 0. So the free energy is 0. So if the free energy is 0, how are the stresses, which would be the derivative of the free energy with respect to strains? 0, no sense, okay? So that is not the contradiction. The contradiction is here. The same variable cannot be simultaneously be free, epsilon can vary in any way, or internal. Why? Because internal variable, the evolution of the internal variable is restricted. Restricted by what? By the evolution equation. So one variable cannot be at the same time free and internal, restricted. Okay? The evolution cannot be any and restricted. So the contradiction leads to that contradiction that the free energy in that model is 0. So nothing can be obtained. The free energy exists because the free energy defined as the Fourier transform of the Gibbs potential exists. But nothing can be obtained from that. The rest of the framework cannot be applied to it. Okay? But we are going to use that. Yeah.
But in the last model, it was the variable is internal as well as dependent.
Okay, but not free. The contradiction is that the contradiction is the same variable cannot be free and internal.
But
And the internal is internal and meshed and dependent, which is not a contradiction. In the sense that, okay, what does dependent means? That it depends on the instantaneous value of the variables. But of course, if it's free, in that sense, it's also dependent. Okay? So the real contradiction is for the same variable being free and internal. But there is not intrinsic contradiction of the same variable being internal and dependent.
But
Okay?
in the last class, we studied that when you did the sets for the free, internal, and dependent, and you said that there will not be any, like, all those who are not free and...
Well, because it's not the same. You're right. You are just looking at putting your finger. Yeah, you are right. I mean, they are different, but the constitutive equation in that previous case here, following the question of your fellow here, that in that case here, sorry, let's go back here. In that case here, I'm going to here, and then here, exactly. I'm talking of two different, maybe I should have taken out this here, okay? I'm talking of two variables. One internal variables, which I don't define, but whose evolution equation is that, okay? And then the constitutive equation says that the value of this variable is the same to the strains, okay? I'm not saying that it's the same variable, okay? Good question anyway, that's a really good question. So, going to that, was here, and then that model, and then, okay. So let's go now to next step. The step with a little more complication. Let's combine in a serial way, elastic model and a dashpot, one after the other, okay? Let's see what does it represent. Okay, so imagine that I have an elastic model characterized by some elastic property C, and a dashpot characterized by some viscosity eta. Okay, and then of course I can consider the strain of the elastic model, and which I call epsilon 1, and the strain between both ends of this dashpot that I call E2. And then I can say that the total strain, since they are in a serial arrangement, then the total strain is the sum of epsilon 1 plus epsilon 2. Okay? Epsilon 1 is the strain of an elastic model, so it could be thought as an elastic strain, and then epsilon 2 is the inelastic strain. So that's a case of one general case of this additive decomposition of the strain-based models that I refer to in sometimes. Okay. Well, I have that. Then again, whenever I have a viscous model, now that I've learned from the previous model that typically the strain associated to a dashpot is an internal variable. Okay, let's call this strain equal to beta as the internal variable. Okay, so okay, this again I have the physical interpretation of the elastic strain, that is the strain in this epsilon 1 in this and this in this model. So it's the inverse of C times the stress. Look at the stress, since they are arranged in serial, the stress is common to those models. Okay, every model has, or every element of the model have a different strain, but the stress is common. Okay, so we can say that strain epsilon 1 would be the inverse of the elastic modulus, C minus 1, times the stress. Okay, and epsilon 2, which is the inelastic strain, is again, since it is the strain in a dashpot, so recalling what we had here, the strain is 1 over eta times the stress in the dashpot. So the evolution, or that equation would be, that strain would be 1 over eta times sigma. Okay? So this is just a justification, or just a first arrangement of the physical interpretation of the model. Okay, let's now formulate the model in the framework we saw before. Okay? Let's do first a strain-driven model. As I say, a strain-driven model, I said that I know that the free variables are the strains. So I consider the strains, the total strain, as the free variable. Okay? Then I consider the internal variable beta. Okay? And then the remaining variables, typically the stress and the free energy, they are dependent. Okay? And the evolution equation for this beta is just this one here. Beta equal 1 over eta times sigma. Just inspired by what I saw in the previous element. Okay? So this part of the model. Now let's formulate the potential, the free energy. The free energy are a scalar, and the scalars are additive. So let's consider that the free energy is the sum of the free energy corresponding to an elastic model under these strains and this under these strains, right? So what is the free energy of an elastic model? 1/2 of the quadratic form in terms of the strength, epsilon1, and multiplied by c, which is the elastic properties of the model. What is the free energy of a dashpot? Remember? 0. What? Why not? 0. Well, 0. It's 0. Inspired by what I saw before. So the total free energy would be the sum. So it would be that plus that. Okay? So I postulate a free energy, which is that plus that. And by the way, this one, epsilon1, is epsilon minus epsilon2. Epsilon2 is equal to beta, so it can be written in that way. In terms of the free energy, this is just a manipulation which aims at representing the free energy as a function of epsilon and beta. Okay, that is epsilon1, but epsilon1, which is that, is epsilon minus this, which is epsilon minus beta. So I postulate, inspired in that, I postulate this free energy. Let us see now what I obtain. What would be the constitutive equation of this model? So what would be the stresses in terms of the strains? Okay? What is the equation that relates the stresses in terms of the strains? Can you tell me?